In the modern cloud, sending text to a large language model, or LLM, is a direct conversion of data into hard currency. Every word processed directly consumes compute cycles, and those cycles are billed back to the developer. But the billing logic of these application programming interfaces, or APIs, contains a massive financial paradox. Sending the exact same amount of human information to an AI can incur wildly different costs, depending entirely on the language of the prompt. This diagram shows a side-by-side comparison of API processing costs. On the left, 1,000 English words registers a baseline token count, dictating the financial cost. When translated into Japanese, the token count explodes. The API bill multiplies by 3, charging a massive premium. This severe inefficiency does not happen in the neural network's deep reasoning layers. It is dictated entirely by a structural hyperparameter called the vocabulary size, which is hard-coded into the model's tokenizer. To optimize unit economics in production, prompt engineering is insufficient. Controlling costs requires architectural intervention at every level of the pipeline, from selecting the optimal vocabulary matrix to engineering systemic data routing logic. This diagram outlines the modern transformer architecture, the foundational neural network design for current language models. We trace where the tokenizer meets the core compute engine, the initial embedding layer at the input, and the final softmax layer at the output. The vocabulary size, mathematically represented as V, dictates how many unique text fragments the model can recognize. Setting V requires balancing sequence compression against pure computational overhead. At the embedding layer, we calculate the exact parameter count dedicated to this vocabulary table. Physical memory equals 2 times V multiplied by the model's hidden dimension. Expanding the vocabulary size from an older 32,000 to 128,000 tokens generates millions of additional parameters. This physical bloat occurs before the model performs a single logical operation. The advantage of this massive vocabulary is speed. A larger matrix allows the model to compress complex phrases into single tokens, drastically shortening the total sequence length of the document. The model's internal attention mechanism calculates relationships between words, and its processing time scales quadratically with sequence length. Feeding it shorter, highly compressed sequences forces the model to read long documents much faster. However, this compression creates a severe bottleneck at the final step of generation. To select the next word, the softmax layer must calculate a distinct probability score for every single token available in its vocabulary. Expanding the vocabulary from 32K to 128K quadruples the math required at this specific output layer. This heavy computational drag directly increases the time to first token, slowing down the overall generation speed. Ultimately, engineers must balance processing efficiency against physical hardware limits. A massive vocabulary consumes valuable video random access memory, or VRAM, leaving less physical space on the GPU to hold the user's conversational context. Translating this low-level hardware math into a predictable API budget requires measuring token density. Token density is the strict measurement of how much actual character or word information fits inside a single billable token. This chart compares the internal allocation of a small 32,000 token model against a modern global model. The small grid is dominated by English characters, while the larger grid has explicit segments for foreign scripts and programming syntax. For English text, the industry baseline is highly consistent. One billable token reliably captures about 4 English characters. Older tokenizers lacked dedicated slots for non-English languages. When presented with Arabic or Hindi, the system would fracture the text, reverting to processing the words as raw, individual bytes. This fallback mechanism is the source of the language tax, guaranteeing a 300 to 500% cost inflation for global applications processing the exact same meaning. Modern 128K architectures, like Llama 3, eliminate this penalty entirely. By dedicating explicit matrix space to global languages, the system absorbs whole Japanese words into a single, dense token. This principle of token density also dictates the viability of automated coding assistants. Older models processed indentation inefficiently, billing a discrete token for every single blank space leading up to Python code. Modern tokenizers, trained on GitHub, contain dedicated slots for common indentations and syntax strings, compressing those 4 spaces into a single billable token. When an API provider announces an updated tokenizer, it is a structural pricing update masquerading as a technical footnote. Maximizing token density allows engineers to process the exact same string of text while heavily slashing the final billable token count. Once token density is maximized at the model layer, developers must scale the production application by optimizing the external data routing layer. This flowchart displays a standard application pipeline. Unoptimized systems push all incoming data through a single, congested real-time processing pipe, exposing two massive cost bleeders: redundancy and urgency. Redundancy plagues retrieval-augmented generation, or RAG systems. RAG is a framework that retrieves external documents to ground the AI's answers. In standard RAG, massive blocks of static system rules and conversation history are resent to the provider and rebuild millions of times a day. To solve this, developers use prompt caching. The system processes the static text once, storing its mathematical representations in the key value cache. The model can then pull these pre-calculated vectors directly from memory rather than processing the text from scratch. Relying on the KV cache drops input token costs by up to 90%, while drastically accelerating response times for end users. The second major inefficiency is urgency. Default API configurations assume that every request must be computed synchronously and returned immediately. Demanding immediate compute forces cloud providers to maintain massive GPU clusters to handle sudden traffic spikes during peak hours, and they charge premium rates to maintain that real-time availability. Developers bypass these premiums by using batch processing for background tasks, like generating synthetic data or executing bulk document translations. By routing non-urgent data to asynchronous queues, developers allow providers to process the workload during idle server windows. In exchange, the application secures a flat 50% cost reduction and vastly higher rate limits. A highly optimized production pipeline actively categorizes traffic based on urgency and redundancy. It routes data intelligently, avoiding the financial penalty of treating all API calls equally. This diagram visualizes the three-tiered optimization stack required to control unit economics. The foundation represents a historical shift. The old mandate for small 32K vocabularies to protect VRAM has been entirely overwritten by modern architectures, prioritizing 100K tokens and above. Mathematically, the heavy computational drag caused by calculating probabilities across a massive softmax layer is a necessary penalty. It is offset entirely by the processing speed gained through raw sequence compression. This large vocabulary baseline establishes token density, processing global languages and generating code at a fraction of the cost. Above this, intelligent routing dictates profitability. Pairing dense models with KV caching and asynchronous batching is the only path to scaling to millions of users. Deploying large language models in enterprise environments requires rigorous systems architecture. Profitability is dictated by mathematical trade-offs at the hardware layer and strict token density management across the entire stack.